Very good afternoon. Am I audible? Yes. Okay. So it was easy for me because my presentation starts now, post lunch, so I had to keep myself awake. So I'm all awake, but I also hope I'm able to keep you all awake. I think since morning we have been hearing very interesting sessions, right from understanding ASPICE, the changes, which is also important. I think most of you here are into development, but also important to understand what's going on there. Plus also we heard from Continental about the trends and what are the changes that are coming in with the trends. Interesting presentation also coming from MathWorks, where we heard towards simulation, what's going on, even keeping pace with the new trends, I think, which is very important, and also drawing the parallel towards the evolution of software-defined vehicle, how to realize that even with simulation, which was, of course, very traditional. In traditional world, it was a lot more scientific. Very interesting presentation that we heard also from Celton Semiconductors. A very different perspective. Putting it all together is what I saw, and also giving us a glimpse of the past, which we often ignore, but only look at the future and where we come from. Also from Mr. Shankar Mahindra, interesting to know what we should be doing, what we should be contributing, and not just look at trends and not just talk about trends. So I have put together some information looking at these trends and trying to break it, trying to simplify it. This is what we do at Vector. We are a company which is into software. We look at always simplifying the complexity. We come from a background of looking at development, software development in automotive, right from 35 years ago when CAN first came into the automobile. And we have been following it. We have been working on newer topics in this technology as the protocols came in. So just a quick view what we do. For people who do not know Vector or have not heard about Vector. In a simple way, we provide OEMs and suppliers of automotives, tier 1, tier 2, all the engineering companies and related industries with a professional and open development platform of tools which are required to develop the embedded systems, software components, and a bit of services around it. That's what we do at Vector. We have been doing this across the globe, and our main focus is always engineers, because there are trends, there are business needs, there are environmental needs, regulatory needs, but engineers are always the ones who have to realize them. So we focus on engineers. All our products and services give advantage to these engineers to simplify or try to simplify this complex challenge that they deal with day in, day out, and break it down and realize them in a very systematic and stepwise way. So quick glance, Vector, very small, globally 4,000 engineers. We are present in 14 countries across the globe, India being one of them, headquartered in Stuttgart, Germany, where all the development happens. And the rest of the world, we work closely with our customers, sitting close to them. Part of several standardization organizations, committees, AUTOSAR, one of them, several ISO organizations as well, committees and open standards as well. Customers across the globe in 76 countries. Wherever we are present, we work closely, else we deal with them remotely. Been 35 years for us, and we see a lot of changes coming up across now in the coming days. We are organized in a very simple way, or rather more from the development process that is existing at customers. We have products into defining E-architecture, developing distributed systems, embedded software components, both AUTOSAR and non-AUTOSAR based, and now SDV, and we talk about vehicle OS now, putting them together. So we have these components that go into the ECUs, HCPs, HPCs that we heard since morning. Testing is our flagship portfolio. The tools around CAN, which have now evolved to become larger than CAN, but still continuing with CAN. There are new bus systems, Ethernet. There are a host of simulation needs, a host of development needs. We talk about it in the next slides that I bring up. Hill systems. Now we talk about DevOps and also code testing, which was not heard in automotive. It was mainly avionics, DO 178 standards and 138 standards. Now it's coming in automotive. Diagnostics and flashing, which is very important for the vehicle. And now looking at remote diagnostics, remote flashing. Calibration being a very control system oriented product, vehicle needs a lot of calibration, post-build calibration, ability to access data, to measure data, to interpret the data, analyze huge amount of data that's coming up during development, during testing and validation. So putting them together, we also offer a host of solutions. So I will not go into detail of that. So looking at what's there coming up for everyone in the room and also for every engineer across the globe are these mega trends, right? So we have heard about them a lot. Connected, autonomous, shared, and electric. We know there are no more future trends. They are already there, connected. There are already 700 million cars that is projected to be connected by 2030. We already have them in most of the cars now. Autonomous, although we heard also from Ms. Lata that it's going slow now, not looking at completely autonomous vehicle, but there are levels of autonomous driving, 2.5, 3, level 3. We foresee by 2030 that there will be 13% of vehicles driven, at least in US, which will be completely autonomous. Shared by 2040, about 80% of miles, which will be driven by shared mobility. Electric, already this year, 600 new electric models. We talked about it in the morning. We heard about, is it going to really continue in that pace or is it going to slow down? But still it's there, a lot of development happening around this. So while these mega trends are there, we hear about them, we listen about them in the conferences, we study about them. But looking at realizing this is what I'm going to talk about. If you look at these mega trends, basically they are driven by consumer or customer expectations, right? They're not more of push, but they are more of, the OEMs are looking at what can they delight the consumer. So Vision Zero is very important, safety. Then autonomous driving, if not full autonomous, but assisted or partly autonomous driving. Exciting user experience. We know, we are sitting now in the world post-COVID, working from anywhere, connected always, even on airplanes. So it's impossible for us to ignore this aspect in the vehicle. So this is coming again from consumer expectation. Updatable vehicle features, and of course, when it is connected, there is always a risk of security. So how to protect it against hacks and ensure the safety of both onboard and also the people outside and the infrastructure. So the industry is looking at this problem, taking this problem and looking at solutions, coming up with over-the-air updates, measures in terms of cybersecurity. There are new developments happening, and new development will also bring in new test system. We cannot test the same way, from the test or development point of view. And then also every development has to focus on both vehicle and cloud as well now. So it's parallelly happening. So suitable vehicle and cloud infrastructure of development is very important. So we heard about smartphone on wheels. This is exactly what the consumer expects. But the solution from the industry is software-defined vehicle, taking the learnings from mobile industry, but then bringing it to the automobile. So if you look at the three main pillars of what the so-called SDV or connected car brings in digital cars, if we just simplify and put it, are the onboard platform, the content that goes in the vehicle, that's there with the infotainment, with ADAS, and all the rest of the vehicle software. And the off-board platform, which is the backend, connectivity backend, the cloud, and possibility to do integration with third parties, over-the-air updates, and a lot of data-driven development as well. And plus, what is most important is the tooling, the developer tooling, processes, methods, and tools for all this software development and maintenance. It's very, very important to rightly define them. So, of course, SDV, when we talk about, it's always looking at cross-domain functions. They are both off-board and on-board, and seamless possibility to shift an algorithm or an application running both on-board or off board and exchange data seamlessly. That's very, very important in the developments, and all the tool chain should support that. And the speed and quality are mainly influenced by this tooling, right? We can always imagine, yeah, we can develop mobile phone, smartphone on wheels, but it's a car, and then there are a lot of apprehensions about releasing a new feature. We need to do a lot of testing. You know, it goes through summer test, winter test, and months of testing, and then is released, right? So cut short all that, and a new feature has to just come out. I think then we need a very strong tooling for that. So what's more important here is consistent tooling, both at the vehicle level or at the back-end level. So it's very important to develop a tooling, and for the engineer, it should be possible to develop both, right? So here is some picture of how a SDV looks like, right? So it's just an architecture example, more or less similar, but there could be deviations. Each OEM would find ways to achieve their goals with a small deviation from this. So we heard about HPCs. So these are mainly looking at very computation intensive applications, in-vehicle infotainment, ADAS, where there's a lot of data crunching necessary, a lot of algorithm running, MIPS, high MIPS, and this is where HPCs come in, all the yellow boxes. And typically they are communicating. They are not really controlling anything. They are not control systems. They are communicating over Ethernet in a service-oriented way, and also communicating with the backend, with the cloud, because they are connected to the cloud. The green ones form the zonals. There could be, again, different configurations. There could be 2 zonals, 3 zonals, 4 or 5, depending on the OEM and the complexity of the car, putting together a lot of varied functions, body control functions, into one ECU. A zonal is a large embedded systems controller, right, with a very high capability. Number of IOs are high, and is still able to communicate both on the legacy world, which is CAN, and as well as with the Ethernet, which is the HPCs. So zonals come in between HPCs and the rest of the car. And they would still communicate on a service-oriented way, but also ability to communicate in a signal-oriented way with the control-intensive issues, which are, of course, the powertrain or safety. So here, there's a lot of years of research that has gone in, and these systems are optimized and developed, right? So we are not looking at putting them in a HPC because there is a lot of computation power there. They would remain. They are safety critical, possibly also a lot of work done on that. And it's better to continue from the legacy into these cars, or maybe some new developments still happen, but let's keep them away from this zonal and HPC architecture. There could be very smaller ECUs which are coming now, also with the new type of sensors, camera, LiDAR, and radar. They are smarter ECUs. They are able to process a lot of data internally and deliver kind of final outcome. And plus very smaller sensors and actuators which would be coming in, which are the blue boxes, right? So this is how the world looks like inside a car, with multiple set of ECUs, smaller, medium, bigger. And what is an OEM looking at it? Because there's always this talk about, I've also heard from semiconductor companies saying, now it's all about OEM deciding what to do, no more tier ones, right? OEM is deciding the chipset, the SoC, which is partly true, but then in what area are OEMs deciding? OEMs are deciding more towards back-end, HPC, zonals, and less towards the control intensive or the smaller sensor actuators. Whereas tier ones, of course, they come with their system know-how. They have built the systems, the airbags and ABS systems together with the electronics and the hydraulics and the actuators. So they come more from that side towards this side. So the influence of tier ones is a lot lesser on HPCs and back-end, but they have to be prepared. Like we heard in the morning in the presentation from Ms. Lata, there's a lot of collaboration also necessary between tier ones, because there could be a software application from a tier one coming and sitting on an ECU or HPC or zonal developed by another tier one because of the OEM demand. So if I go into the vehicle itself, how the software is layered and structured inside each of these type of ECUs, it may look like this, a bit complex diagram, but try to simplify it for you. Something that has emerged with the SDV coming in is the base layer, which is again mix of several technologies, AutoSAR, adaptive AutoSAR, POSIX-based operating systems, Android, and whatnot, right, to achieve whatever is the goal of the OEM at the application layer level. But then how do they look like? If you see a smaller ECUs, the blue ones which we saw, the sensors or actuators, they would typically have just the basic application, maybe AutoSAR or not even AutoSAR, and directly the application that is necessary to control it. The other ones, the red ones, which are maybe a bit more control intensive, the powertrain or the safety ECUs, they would still have a microcontroller, a bit more powerful. And AutoSAR classic running there, MicroSAR is the vector trade name for AutoSAR. And then, of course, the applications for AutoSAR, there could be security necessary there, so HSM comes in, and then there could be switches which are required between these networks as well to deal with the CAN and Ethernet and so on, and multiple Ethernet switches, right? Now, if we look at the yellow boxes, the bigger ones, the HPCs, and also those boxes which at times also zonal. So there could be now, there is definitely a need of microprocessor, no more a microcontroller. The computation is very high, data intensive. There could be possibility that the microprocessor and microcontroller would coexist on the same board in HPC, because this is a kind of intermediate steps OEM is looking at. They are still keeping the microcontroller in HPC because we have never lived in a world in the car with only microprocessors so far. We are microcontroller people, so some applications it's easier to run on microcontroller. But ideally, a HPC should have a microprocessor and then multiple operating possibilities, multiple operating systems running different types of applications, ADAS middleware, you see IVI middleware, vehicle intensive. Adaptive AutoSAR is also an attempt from automotive industry to bring in the POSIX capabilities in the automotive. And then on the back end, when you look at on the back end, there is also the back end its own evolved. We look at the cloud there, so coming with the services from the cloud vendors. But it's important that the applications which are on the top, the blue, yellow, the orange, and the red, so it's important that these applications are developed with the capability to run both onboard and offboard at times. And there could be applications which are maybe complementing, applications meant for a specific onboard purpose would also be there in the offboard and talking and exchanging data for that reason. So this is just to give you a picture how the configuration looks like in the software, and what every OEM is looking at is defining that base layer and calling it as vehicle OS, and then making it available for the app developers further. So this is an example what we really did with an OEM. So where multiple, again you see the greens, and of course there's a bit of color change here. Zonals have become blue, and then the orange, which are the high performance ECUs. So we have different approaches that we took, very basic, small, lean stack. Then there is a little bigger one in number 2, which goes in. So if you see the smart sensors and actuators, they would be fulfilled by this basic stack, a roof controller or a steering wheel switch controlling and so on. Then the higher applications like engine control and ABS would have also the lean stack, and then running the AutoSAR application on top of it. And when you look at zonals, which are still microcontroller based, which are bit bigger ECUs with a lot of IOs, so they would have a concept of platform. You would build a zonal platform concept with ability to deal with variants and multiple applications. And then bring in a base layer when you look at the HPCs, which are microcontroller plus microprocessor based, which would be, let's say, for applications like ADAS or IVI and so on. So this is how we realized for an OEM with the AutoSAR and adaptive AutoSAR applications, and bringing the platform concept for the overall vehicle architecture and addressing host of ECUs. So what you see here is again a lot of reuse, right? So 1 and 2 is still there in HPC, in zonals, right? So 3 is there in HPC as well, right? So this is how the software middle layers get reused across all the different ECU types. This is giving an overall picture. So we talked a lot about the base layer and the vehicle side, including the cloud platform. What is important is the middle one as well. When you talk about SDV, which we never hear about a lot, is the software factory. You have the complex operating systems running, you have the ECUs and HPCs there in the vehicle, and then the intention is ability to do over-the-air updates, development even after production, add new applications, or open up sort of app store for a very smart app developer out there in the market like they do today for the mobile industry, right? So what's important is to be able to build the overall development process, put up a tool chain in the overall development process, which is nothing but the software factory, where it is looking at the vehicle campaigns, builds, CI/CD, DevOps, host of things put together and making it more like a, a kind of software factory assembly line where, the applications are getting developed day in, day out, post-production as well. So it's important to look at automation here. A lot of concepts from IT are also borrowed here to develop this software factory. A lot of ecosystem, multiple players, multiple tool chains, simulation tools, testing tools, development tools have to go in here as well. And plus, what's important is the last parameter, the advisory and supporting services. So industry, in the past had very clear competency, divide. There were engineering service companies which were very good in engineering and, fundamental, engineering concepts and developing ideas and solutions which are not really products but solutions which are taken by the customers. And there are tier ones, if you see, they are very system intensive, focusing on a particular domain, developing the mechatronics, the electronics, and the software for that completely, and taking it as a black box more or less to the OEM, right? And then there are OEMs who are having the concept and idea of the vehicle, bringing in the vehicle features and putting together multiple suppliers' products, and then bringing the vehicle out in the market, right? Each one had own competency. But now it's really converging, or it's really, each one has to learn the other. Right? The company like Vector, who was developing software all the years, now has to understand how the vehicle campaigns run. How do we build a CI/CD system for the OEM? And it's important to understand also for the tier ones to really see, how to interact with the other hardwares coming from other tier ones, right? So, and OEM, they have to learn about software. So it's converging. And it's not the idea to, just do everything in isolation. It's important to bring that together. And that's where advisory and supporting services come. So Vector works with several OEMs globally, as well as also in India. We have worked on developing the SDV architecture, conceptualizing it, preparing it as per the OEM's use cases and OEM's goals, working closely with the OEM, not trying to say, hey, I have the architecture and take it and then it works. No, it has to be developed together with the OEM. Based on the OEM requirements, OEMs have choices on the hardware side, what they want to choose. They have choices on the supplier ecosystem. So they also look at the application use cases and the cost and so on. So they are custodians of all that, but they also want to understand how is this architecture evolving. So we work closely with them and come up with an architecture, and then we continue to work with the OEM along with their tier ones to make sure it is a success. That's what Vector does. So look at the collaborations we talked about. So this was there in the past. The entire ecosystem is still existing. It is same more or less, not much changed. There's a lot of talk about vehicle OEMs becoming software companies. Of course, the roles, the competencies have to be developed to learn the other aspects. But then this is how the flow was, right? It was more of a waterfall model. So tier 1 supplies to tier 2 supplies to tier 1, then to OEM, and then it goes to the end customer. The collaborations were simple. There were a lot of interactions between these multiple players in the ecosystem, and then the product was developed. But with SDV, what's happening? The entire product lifecycle changes. So if you see in the bottom below, so there is development. Of course, startup development happens. But then when the series release happens, so there is a maintenance phase and then end of life, right? So there's a very controlled sample shop that is happening. But with the SDV world, it's completely DevOps in a simple word, right? It's continuous, so there is a series release happening, but then there is development still going on, and then new software releases coming up as the vehicle is on the road. So after all that, I just wanted to focus on the validation side to understand deeply how is the validation now looking at when we look at SDV or even the modern mega trends, be it ADAS or connectivity. So there's always the focus, which is system under test, which is either a single ECU or a set of ECUs, testing them together, or the entire vehicle. So this could be system under test. And we look at putting around it a kind of environment which is bringing in real-timeness, and where there is everything real. If not available, then we connect the actuators, we connect the sensors, and then put up a hill system, which of course needs to be configured, which needs to also run a lot of simulation models. If there is an absence of an ECU, you need to simulate that ECU in a closed loop way at times, or open loop. So there has to be also the test environment, the experiment, which is a desktop, A lot of automation is necessary, test case writing, analysis, and reporting, and all that happens in the online area, while this could happen on the offline area, right, including certain part of analysis. So this is how a typical hill development looks like, and hill environment testing looks like. What do we see when we move to SIL? The idea is to keep it more or less similar. It has to be same because the software under test could be a single ECU or set of ECUs, but then rest of it all is virtualized sensor, looking at models, bringing the sensor models and running it. Virtual ECUs, we talked about VECUs in the morning, virtual actuators, and also the rest of the simulation environment. Now, the tests, what you see important is the rest of the blocks are same, be it a hill or be it a SIL. So it's more or less similar to hill. Now we talk about shift left testing, right? So it's not just about shift left. It's also important to look at shift right as well, which means what you are testing in the simulation environment, you should be able to run in the hill environment. And because, if you look at the software-defined vehicle development, there is no, develop, release, and production concept, right? So post-production, there is again development going on. What is tested on hill should also be tested on SIL because you're adding a new application. And then it should go on a hill. So it should be back and forth. So it's very important to create an environment which is more or less similar for both SIL and hill, and then continue the development, continue the testing, continue the release. Because if you see in the DevOps cycle, there is release which is on the right, but development is also happening continuously, right? So it's very important to set up such a testing environment which supports both hill and SIL in a seamless way. I think I can go in detail about benefits of the virtualization. We all know it's very important now, and it's not just to say no more testing on the real hardware or real vehicle. That is always there, but it's important to bring in virtualization because then we are able to test early. We all understand, right? There is not like a sample, B sample, C sample concept now anymore. Like while it's in SOP, there are new applications getting developed, new ideas putting in the ECU. So it's important to be able to test them continuously. So virtualization is very, very important for that purpose, while we still go ahead and test on the real hardware. So I'll skip on the advantages of virtualization in interest of time. We all understand, just to highlight a few. It just brings in, I'll show a very interesting graph in the next slide. Defects caught early, cost is definitely an advantage. And you don't need the real hardware. You can do a lot of testing as you code or develop. So you can also look at creating fault scenarios in a safer way rather than in the real environment. And of course, there's a lot of possibility to auto-generate test cases and reuse these test cases further across in the testing process. This is something that I wanted to highlight. If you understand here, typical development phase, coding, unit testing, functional test, system test, and release. In this entire cycle, a lot of defect injection happens during coding because that's where development is happening. Rest all is testing, right? Defect injection may not happen during testing a lot more, or functional test or system test, but during development, a lot of defect injection happens. But where are they found? Is typically at the later phases. When you do unit testing, you may be able to find certain defects. Functional testing, system testing, even after release, there would be defects found, right? So that's the reality if you just rely on the process of testing that is described here. And when you look at the cost of repair, it goes up 1x, 4x, and up to 600, more than 600 times after release, because you have finished the development, then it's released and fixing it, and again you have to go through the entire cycle. So the cost is very high. So what does shift left look at is trying to bring in a lot of testing ability in the earlier phases, which is unit testing. So where you are able to capture a lot of defects early. So that's the solid orange line that is seen here. So if you are able to find a lot of defects in unit testing, how do you find a lot of defects in unit testing? Is to create the real scenarios, bring in a lot of virtualization, right? Focus on testing the functions and bring them up here, and then of course continue your functional testing and system testing on the real hardware, right? So the idea is to do that with the possibility of shift left and shift right as well testing. So the concept of shift right is again basically reuse all your effort that you have put in unit testing in creating test scenarios, run them on the real environment as well. So it should be possible to do that both. the tool chain should support this. That's very, very important. Talking about ADAS, I just brought in a simpler view on what is the focus of ADAS validation. So a lot of development happens in ADAS where it's important to do a lot of measurement during development. So we need a very good high-speed measurement capability, because here we are talking about ADAS. It's not just the data running on CAN or captured on a I/O port. It is the data which is streamed video. So it's very important to be able to capture high-speed data from the ECUs. So we need a very strong ability to measure the data and do a calibration as well live. Logging is very, very important. The data logged in the field, captured with a test vehicle running, the street data or the road data, it's important to analyze that. So we need a very intelligent and maybe kind of big data analytics tool like Canopy, which is able to read this and put it in front of the development engineer with various scenarios, triggers, and so on. And also the road validation. It's very, very important. Now, once you have the log data, you should be able to run this in the real environment in the ECU. ECU gets to see that, yes, there is a real sensor data coming in, and how do you validate it? So you should be able to validate with the real recorded data and also the analyzed and ECU interpreted data in the same way. So, and to correlate that in real time. That's very, very important in the ADAS data validation. So the speed of data acquisition is very important here, and the precision of measurement is very important here. So I just put up a kind of setup that typically we look at when you do the ADAS hill or replay testing. So a lot of data that is recorded is run by this VP64 or 75, this kind of replay station, where it is able to support 10 gigabit Ethernet data transfer. And through the high-speed interface, which is the VX interface, it goes to the ECU. So typically what in a real vehicle environment, this data comes in from the camera sensors at a very high speed to the ECU. So either in the format of GMSL or FPDL formats. So it's important to have this data coming to the ECU over CAN and over these specific protocols, and monitor this as well, how the ECU is receiving it, what has the ECU received, and how is the ECU behaving. So again, you need a control which is there in the software, which is CANU, which is running on a separate system, which is observing this replay, is able to control, trigger it, set triggers, set conditions for the ECU, and then also read the ECU behavior through a hill system and see how is the entire closed loop testing possible. Now, this is entirely in the lab. Of course, the data recording is really done in the field from the recording loggers and so on, but that's replayed here, right? So imagine doing this on a real road condition. It's very difficult, right? Live with the car running on the field. So this is one system that really looks at entire simulation, running the tests both in the sill and hill environment. So you can also just remove the hill and just do the replay and understand what's the ECU behavior, or bring the hill and see in a closed loop way the real hardware, how it is behaving. Yeah. So I stop with this, open for questions, and try to just put an image of how the development looks like, trying to simplify it, but yet it is still a lot more complex. Yeah. Thank you very much for your attention. So if any questions, I'm around. Yeah.
Hi, my name is Prem from Bosch. So I have a question related to the cloud which you've shown actually. Is it related to anything with Amazon or the existing partners, or is it a separate server or cloud with Vector team?
This is the cloud the OEM chooses.
Okay.
So this is, you're talking about SDV cloud, right? Yeah. So this is the cloud OEM chooses.
Okay.
It could be anything.
So the tool will be compatible across any type of cloud?
The tools are compatible for any cloud, okay. AWS or Azure.
Okay.
So, yeah.
Thank you.
When you say that the other slide on the software factory, is it you're talking about mainly on the application level, or you're talking about all the layers like services, infrastructure, that also will go to the software
exactly.
factory?
Software factory is all the layers.
Entire.
Entire.
So
Yeah.
it will support directly from the drivers at the chipset level till
Exactly.
application.
Exactly.
Oh,
Yeah.
just the clarification.
Hi, this is Beamsen from MathWorks.
Hi.
So, in your presentation, we didn't hear about AI and Gen AI, to be very honest, because
This is what I'm showing is real, what is going on. As of
reality,
now,
yes.
we are working with OEMs. We have never come across AI getting used in the vehicle side, but we are looking at within Vector to bring in Copilot
That was
in
the question I
creating
was
the
actually just
test cases and running it along with the test case auto generation and so on. So we are working on it. We are not ready yet. Yeah.
Okay. Okay, thank you.
Talking about post-production cost for fixing a bug, right? You mentioned it is 640x.
Oh, okay. Yeah. Test.
With SDVs, do you see that number drastically coming down?
So I think that's true with SDV or without SDV. But what is it focusing on is mainly, how much you are capturing the issues in early phase rather than waiting for. So even today, we see, a lot of vehicle development during the time. There's a lot of data logging happening in the field, right? Because, the issues are coming up in the field. There's not a lot of front loading that is done in development testing, and that's the reason issues are coming up in the field, right? So that's as simple as that, sending an engineer to a remote place, sit there, capture data, come back, and then fix it, and then make another release and flash the ECUs in the field. So those are the factors that are affecting the cost. And this would be maybe easier with SDV because we have OTA there. So over the air, you can do the fix and update. But then it's important that the fix also is tested well, right? And so SDV has to look at a lot of early phase testing and release because we are dealing with the DevOps and pipeline there. And I think OEM has to just in the end qualify whether this is ready for the OTA update or not. Right? Callback, recalls, and everything, right? Yeah, yeah. Exactly. Exactly. At least for those software issues, which could be fixed with software fix, you don't need to recall or call the vehicles to the service station. You can flash it over the air. That advantage is there. But then even to do a flashing campaign, there is a cost involved. So focus on front loading is very, very important. I think I may not be an expert to talk about the exact metrics or the cost parameters, but virtualization, because I've come across at different customers, the focus they have, should also look at practicality, what's really required and to what level we do it, right? If you just leave everything and start virtualizing not just the basic software but the application software, is that really necessary, right? It's important to create a balance, right? So, and not virtualization definitely is not with the intention that the hardware is not available. In the SDV world, the hardware is developed for lasting for next 10 years, right? So it is performance capable, it's ready. So there's no need to worry about not having the sample ECUs or something. But balance is very, very important, I think. Not trying to get into virtualizing everything, right? And create a balance, and you can keep the closed loop, right? As you test in real scenario, if you are able to improve your virtual models, continuously do that and do a lot more front loading, not to really replace the real testing. Right? That would also follow, but here we would capture a lot of issues early. That's the whole idea of virtualization. Yeah, I'm sorry I may not be able to give the metrics. I'm not industry expert in that way. We go with the real scenarios. Yeah. Sure. Okay. If no more questions, thanks a lot for your time. Thank you.